Hello everyone, my name is Pascal. I will present the subject string shooter for Team Universite de Lyon. So a string shooter is a simple apparatus which consists in a string of loop fed between two control rotating wheels which rotate at the same speed. So here is the experiment in motion, in video and in live. You can see, as you saw for a brief time on the video, the string rises in the air and acquires a well-defined stationary shape. And if you tap on the string, you can see waves propagating. So the question that was asked by the IPT committee was to explain first the overall shape of the loop and then investigate the propagation of waves on the string. So there are two parts to the question. First, we'll answer the first part. So let's do a preliminary analysis of the shape of the loop. So the parameters explored that you can vary on the system and that are relevant that we determine were the string velocity v, the string length L, and the linear mass mu, which gives the weight. With these parameters, we form a dimensionless number comparing the kinetic energy and the potential energy. As you can see here, the linear mass cancels out, and we are left with v squared over gl, and the purpose of the next slides will be to investigate if we describe the system or not. First, let's introduce one notation, the angle at the furthest points, which is defined by the angle between the vertical axis and the line that goes between the wheels to the furthest point on the string. So this will enable us to compare different shapes quantitatively. We plot this angle that we just defined as a function of the string velocity. Here, you can see that for low velocities, the string is vertical, it's as if it's at rest. Then, when you increase the velocity, the string rises in the air and eventually reaches a horizontal position. So, by varying the velocity v, we can explore a large range of angles, so there is a strong dependency. However, here we doubled the string length, but the curves are almost the same, so there is a very weak dependency on the length L, which is the first indication that this dimensionless number is not really relevant. Next, we define V45, the velocity required to rise the string at 45 degrees. We measure this velocity as a function of the string length. And we did so for two different linear masses of one order of magnitude in between, a lighter one and a heavier one. As you can see, there is a strong difference between the two. But there was no mu in the dimensionless number. So this shows that this dimensionless number does not capture all the physics of the problem. So to understand this better, we do a momentum budget on a moving piece of string. So we have to collect its acceleration, the differential of tension at both sides, and the gravity. So because v is a constant, you can plug this term into the derivative, and it's equivalent to shifting the tension by a constant mu v squared, and we are left with the same equation as a catenary. And this catenary equation has a solution, so the hyperbolic sign, and the integration constants only depend on the boundary condition. So if you hold a piece of string here, the shape is only determined by the boundary conditions. And there is no dependence on mu and v in this solution, but experimentally there is, so there is a disagreement. And the solution to this disagreement is drag. So we will show you with this experiment. We put our apparatus in a vacuum chamber, and we gradually pump the air out of it. So for a given velocity, at atmospheric pressure, the string is horizontal. Then when we decrease the pressure gradually, the string goes from horizontal to vertical. So this shows that clearly aerodynamic forces have an effect. But what is the effect of aerodynamic forces? Well, drag is a force that is directed tangentially at every point of the string opposed to the movement of the string. Because the string is a loop, we expect the resultant force to be close to zero. Moreover, there is no lift on the string because of its axial symmetry. So the net effect of the aerodynamic forces is a global torque, as you can easily convince yourself by following the arrows, directed counterclockwise, opposed to the torque of the weight. So in fact, here qualitatively, we can already understand that it's drag that elevates the string in the air. Now, more analytically, we get back to our equations. So here we only put tension and gravity and recall that we get a catenary equation that does not depend on the parameters mu and v, with phi being the angle with, of the tangent vector of the string with the vertical axis. However, if we put in drag per unit length in the equation, then our equation is modified and depends this time on a dimensionless number alpha, which compares the strength of the drag per unit length and gravity. So here we retrieve the dependency on the linear mass mu that we saw experimentally, and the dependency on the velocity through the linear, through the drag term per unit length. So this, in fact, is the dimensionless number of the problem. So we solve this equation numerically for different values of the parameter alpha, and as you can see, there is a very good agreement with experiments. So this concludes the study of the stationary shape of the loop. Now we move on to wave propagation. So when we tap on a string, at the top of the string you can see there is a bottom wave that is created. These two waves, these slow waves, are stopped when they reach the turn, and top one propagates downstream. Okay, the top one propagates downstream, and the bottom one propagates upstream. So we will explain these three observations. So for the first one, first recall that for a string at rest, if you excite it somewhere on the string, then you will see a propagation propagating to the left and to the right. But if the string is into motion, to get the apparent speed of the waves, you have to just add the velocity of the string. In some cases, this can lead to a slow wave and a fast wave. So a slow wave you have already seen in the video before. Here I will show you the fast wave. Here we film transversely and we blow on the top part of the string to create a wave. You can see the whole string shifts to the right of the frame almost instantaneously, and you can see the slow wave at the end, but the string doesn't shift instantaneously, it shifts at the speed of the fast wave that will be colored in the red here. So we blow on the string, whole string shifts to the right, and then the fast wave is reflected on the wheels and gives birth to the tiny wave at the bottom that you see here in green. So the bottom wave is born from a reflection of the fast wave on the wheels at the bottom. Now on to observation 2. Why do the waves stop when they reach the turn? Well, if we use our momentum equation projected on the normal vector, we get an expression for the tension that is simply a constant mu v squared plus a term that depends on the position on the string. If you evaluate this equation on when the string is vertical, you get that the tension is mu v squared. So recall for velocity addition by approximating the velocity as the same expression for a meld chord. Then you get that apparent velocity vanishes at phi equals 0 and the string is vertical. So this shows that the slow waves indeed stop when they reach the turn. You can see on this video, if you blow, the velocity of the wave goes to 0 when it reaches the tip. Now we'll explain why the waves at the top are downstream and why the slow waves at the bottom are upstream. So we use exactly the same ingredients, the velocity profile, the tension profile and velocity addition. So at the top, if you evaluate this expression when the string is at the top, so phi is between 0 and pi over 2, the tension is less than mu v squared, and so the apparent velocity is positive. So in our convention, this means that the waves at the top are indeed downstreams. And similarly, at the bottom, the second term is this time positive, so the tension is less than mu v squared, and so the apparent velocity of the string is negative. So the waves at the bottom are upstream, and you get the limit case where at the tip the velocity is 0. So to conclude our presentation, we show that it is drag that is a driving mechanism for elevating the string, which is counterintuitive because it's traditionally a force that is opposed to the movement of objects. We show that the parameter of the problem is the one that compares the drag term with the gravity. We derived an equation of the stationary shape. You can see it very well, but it predicts the shape of the loop. And as for wave propagation, we explained why there was upstream and downstream waves, and why the waves are stopped when they reach the turn when the string is vertical. So thank you for your attention.
Good morning, everyone. My name is Voronin Kirill, and I am a point from Russian IPT team. Today we are discussing problem number 13, string shooter. First of all, I want to mention that problem was solved, but I have several questions, and I noticed several disadvantages that I want to discuss now. Firstly, let's summarize the let's summarize advantages. The speaker demonstrated us experiment. We could observe the form of loop and wave propagations of waves. There were experimental data and some theoretical analysis for the shape of root of loop. Also, the speaker told us about propagation of waves and showed qualitative description of this, but there were not estimations for wave speed and were not any measurements for wave speed. And also only waves in surface of loop was discussed, and for example, speaker did not mention the waves in the waves perpendicular to surface of loop, and the other important point is that in all measurements, angle of roof were less than 0. But for example, in video that we could see on this problem, here was all angles, and particularly angles more than 0. And then I want to mention several questions that I want to discuss. Firstly, how the drag force depends on pressure. You show that the dependence of drag force is the drag force depends significantly on pressure, but you cannot demonstrate any consideration why it is so. Also, what do you think about perpendicular waves? With which how is the speed of these waves, and how it depends on significant parameters. Also, you said that the drag force is the force that allows loop go up, but what do you think about critical drag coefficient? Thank you. Let's discuss.
So thank you for your remarks. I'd like to address first the question that you mentioned here. How does the drag force depend on pressure? you have different expressions of the drag force depending on the Reynolds number. For example, if you consider a sphere with a relative wind blowing at velocity v, at low Reynolds number, it's common to approximate the drag force as proportional to v. You put a radius of the bolt for geometric function, but the important part here, this is the viscosity of the fluid, and it depends on the pressure. So when you change the pressure, you change the properties of the fluid, and so you, for example, in this case, viscosity, so it changes the linear drag force, and when the Reynolds number is higher, it's proportional to this time the density of the fluid, which is reduced also when we lower the pressure. So in different cases, when you diminish the pressure, you modify the properties of the fluid, either viscosity, both at the same time, and this changes the drag force.
What mode in this case did you calculate the Reynolds number?
You can estimate it by you can estimate it quickly. It's actually in the frontier between these two models. So you need a characteristic length, so 10 to the minus 3 for the width of the loop, and v, so it's L. U, the velocity of the string is about 10 meters per second, and then the kinematic viscosity of air, so 10 to the minus 5, and so it's about 10 to the 3, and it's a bit of in-between region in most of the cases. So it's hard to have a universal description of drag. If you remember the graph, at low velocities you need to have this model, and at high velocities more this model.
Okay, I think this Reynolds number is enough to go to this mode, or do you think so? Or you think that this mode is possible?
It depends on here I put a typical velocity 10 meters per second, but of course, if at the beginning, if your velocity is small, 1 meter per second, you'll be more in this region. And if your string is, you can take limit cases in the string. If the string is horizontal, it means you put a lot of velocity, so typically more than 10 meters per second. So I agree with you. This is the appropriate expression. But when the string is close to the vertical, it's more this expression that will be relevant.
From what Reynolds number does turbulence mode start? How much Reynolds number?
It's 10 to the around this region, 10 to the 3, maybe more 10 to the 4 in between these two. So when you have this, when you have velocities of magnitude 10 meters per second, 20 meters per second, then there is turbulence. But this is an effective force which does not account, which is an average of the microscopic turbulence around the fluid.
Okay, did you estimate this coefficient?
In fact, when we do our fitting or a numerical fitting, we fit a value of alpha, so the drag, it's drag of the weight basically. And so when we choose the right alpha to fit the curve, we measure the drag force. So we measure this term. You get alpha, so you get the drag, so you get this. And because we measure the velocity, then we get.
Could you give numbers for your case, for example, for any velocity for this coefficient? Did you calculate or estimated it?
I think if I remember well, the drag coefficient is around unity for our range of operations.
Okay, and is the critical coefficient that allows to go up for loop? Critical.
Well, it's not the definition of critical coefficient is delicate because the transition is not pitch fork transition, so there is not a critical point. Instead, it's more smooth transition, and so it's difficult to determine, to define a critical value of the coefficient.
Thank you.
So overall, it was an excellent discussion between the reporter and the opposer in terms of the points that were discussed from the reporter's position. Having the experiment was an excellent inclusion. I think being able to get some experimental data and actually apply it to the model was a wonderful thing to do. I thought the use of the experiment in terms of especially the vacuum component, so trying to determine experimentally what the key factor was in terms of the string shooter's motion was excellent, and being able to do an experiment to show that it was actually drag that was causing that particular shape of motion was wonderful. There was a good analytical model as well, which was evidently refined, and you developed it through your, first of all, your theory, and then going into the experiment, and then moving back to the theory again to try and refine it further. From the opponent's side, you had some insightful points from designing, from the design of the theory and how the reporters approached the theoretical model. I thought it would have been interesting to hear more about what your opinion was on the actual design of the experiment and how the experiment affected their refinement of their theoretical model. And there was also a good point that you made about having a positive angle on the string shooter. So it would have been interesting, I suppose, to see more about when the string shooter was angled in a positive direction, how that would have affected the design of it, how that would have affected perhaps the theory, the design of the experiment, if there would have been any other forces which would have come into play at that point. Overall, I think both sides presented like very valid arguments about how the experiment was designed, how it is possible to use different experimental techniques to prove your theoretical models. And overall, I think as well it would have been great from the opponent's side to see more of a discussion about those vacuum models in particular. In terms of the vacuum, I think being able to decide that yes, it was drag that was the key player in the motion of the string was excellent. Apart from that, I think that covers most of the points that both sides presented. I think you both did an excellent job. Yeah.
So maybe you can address your point that you wanted to discuss about the angle of the initial angle of the string shooter. How does it change? We didn't include it in our presentation, but changing the initial angle is just a change in the boundary conditions. So in our model, we have differential equation that is a first order, but coupled with you have an equation on first order on the angle, and first order and another equation on the tension. So the angle of the string shooter will gives the boundary condition on the equation for the shape of the loop. So it's in our model, it's just a change of boundary conditions, and experimentally there is no new physics added when you tilt the string shooter.
Does the opponent have a response?
Okay, and also I mentioned that you did not discuss waves perpendicular to the loop, and let's try to let's discuss it. What do you think about waves perpendicular to the surface of loop? About the speed of these waves and how it moves. Because we could see that on video attached that was attached to the problem.
Okay. So actually, in this video, we created a wave by blowing perpendicularly to the string surface. And these waves, so you can see the two slow waves, bottom and top, and the fast wave with the. Sorry. Okay. Sorry for the technical problem, but here we blow on the wave. We did indeed create a wave transverse to the string surface, and it's very consistent with our predictions. so the direction of propagation of the slow waves and the reflection of the waves. So to us, there is no difference between blowing in the direction of the surface or perpendicularly to the surface.
And the other questions let return to the form of loop. Can you open the slide with this? For example, this slide. Yes. Here we can see the dependence of loop of form of loop on drag force. What do you think? Do all alpha coefficient allow to get a stationary form of loop? For example, not vertical form. I mean.
We did run into some trouble solving numerically the equation for example, non-integer values of alpha, but it's more linked to the method of numerical resolution more than the physics. Physically, there is a continuous spectrum of values of alpha that so you can go to vertical position to horizontal position smoothly. There is no singularities, so this is a problem on the numeric side, but not on the physics side.
The whole teams can discuss.
Yes.
We have seen during the demonstration that rope has been torn. The question is, how often does it happen, and what point does it happen usually? Maybe it is due to difference of stress in different parts of the rope, or maybe over where you connected the ends within the same number.
That's a good point. It's a very technical, it's a very challenging it's a technical challenge to be able to have a string that is connected and can sustain several seconds of rotation, and it breaks more often, almost always, at the point where the junction is made. So we use just a knot, and you can see that when a knot gets between the two wheels, it creates a parasite waves, and it breaks when the tension is maximum. So the tension is maximum. Tension is maximum at when the loop gets back into the wheels. So here, because it's here that the string is pulled the most qualitatively. But in our equations, we can also deduce this.
We have one more consideration that can prove that mode of flow in your case it took turbulent. As far as we remember, the viscosity of air doesn't depend on its pressure, because air can suppose ideal gas. This means that if you had Stokes formula in your equation, the form of the rope wouldn't have changed due to drag force, wouldn't have changed in case of pressure change. However, density depends strongly on the pressure. This means that your mode is turbulent. Do you agree with such statement?
Yes, I would think so. For low values of the velocity, so if you use the Stokes formula with the viscosity as a parameter, yes, there is a very low variation in the viscosity as a function of pressure. But when you are in this low velocity regime, when you have to use the Stokes formula, the string is vertical, so you can't. So in our experiments with a vacuum, when the string is horizontal, you use turbulence. I agree with you that that's the force which is quadratic in V. But when it goes, when it is vertical, you use the Stokes formula, but it's already vertical. When you change the pressure, it will stay vertical.
What about inner friction in the rope?
Inner friction? What do you mean by?
I mean friction of fibers inside the rope. Have you estimated its effect?
not within the rope, but I think the more important friction is between the rope and the wheels. When the rope gets between the two wheels, the rope each time is worn out. So it's the same as running scissors or repeatedly. At some point, you get fluffy strings coming out, and this will change the drag coefficient, because the drag coefficient is very dependent on the nature of the surface. If the surface is smooth, the drag coefficient is less. If the surface has strings coming out, then the drag term will change. So over time, the shape of the loop will change because of the deterioration of the string.
Okay, and I have other questions about the rope. For example, when rope bends, especially with small radius, some forces could appear, bending forces. Did you estimate what errors could be related to this effect?
Yes, it was not mentioned in the presentation, but it's an important effect for the fine detailing of the stationary shape. As you can see here on the tip, it's not a smooth. It has a change of curvature. Here it's curved downwards. At the tip, it curves slightly upwards, and this is due to the fact that you can't fold a string perfectly. At the folding, you will have a minimum radius of curvature, and this is a very, very small effect that it's over time, and we didn't miss.
What is the high-speed limit of your experiment, and why did you go higher in speed?
So in our case, there is a practical limit due to the rope breaking. If you go at high enough speed, then the tension that the rope is under stress is too high, and it will break. But and the deterioration of the rope, as we mentioned in the discussion, will appear sooner, and these effects also reflect it reflects on the stability of the rope. When it's too deteriorated, it doesn't have a stationary shape. And also there could be there is a limit, a theoretical limit. When the speed is too high, the tension between the two wheels at the entrance can be negative. So the string, which means that the string is pushed around itself. It does not make, it's not under stress like this, but is pushed like this, and so we do not get a stable shape.
Okay, Stefan, and then like this.
Oh, okay. So I'd ask the reviewer, what is your take on the completeness of this solution?
I think not being able to have an analytical solution in terms of substituting in values and then finding results, especially on the graph that was presented before regarding comparing the experimental results to the results given by the formula. It would have been great to be able to have a model which could have values from the theory substituted into them to find out whether or not they actually correlated. But having that general model was excellent. I think in terms of overall theoretical design and then implementing it in the experiment, I think the result that was given at the end in terms of identifying drag as the key player was excellent. I think it would have been great to see perhaps some more value-driven solutions in terms of, okay, we're doing an experiment, we're going to collect data and then substitute that into the equations to find out whether or not they actually hold.
Thanks.
Actually, I have two questions, but
Only one of them, please.
one question.
Yeah,
So I asked to the opponent, so during this interesting discussion about all these coefficients and order of magnitude, it seems like you're not totally agree with the opponent, the reporter work. So did you work on part of the theory about that? And is there another explanation?
you should not ask these questions because it's not regarding this physics, this round. So
Ah, okay.
because it's not relevant.
Okay.
So you can ask this afterwards.
Okay. So that's it. Teresa?
Okay, just related to this one. So do you have a different opinion on the pressure role on the drag force?
What?
On the pressure role, which you asked a bit in the two different regimes. Do you have a
Yes.
different opinion?
Yes, we estimated the Reynolds number and possible modes of motion, and we think that only this regime could be in this system.
So okay.
Okay, I have a question for the reporter. Can you go back to slide 17, please? Okay, this one. My question is, why are there two graphs? Why are there one? And what did you try to?
We did
do something?
actually try. Sorry about the quality. It's on the conclusion. Oh, it's here too. Here is in this case we fit our coefficient for we fit the best coefficient into the equation to get the desired shape.
So what do you think of this fit? Is it okay for you? What about the coefficient alpha?
In my memory, the coefficient alpha is reasonable. You can check it. You can check if the velocity that you find with alpha is consistent with the velocity that you put into your system,
This should validate if you're in a low Reynolds regime or high Reynolds regime.
It's a bit complicated because in our model the drag is constant. So this coefficient we treat it as a constant, so we can't know the source of which formula is the better one.
Stasia.
You told you made some fitting, so you didn't get the CD properly, and you're doing it. You're taking it from the experimental fitting, the coefficient, drag coefficient.
Yep.
Yeah. Was it changing during your experiments, or was it constant? Was it constant or you wrote?
Okay.
It was fitting that you didn't control it.
It was the fit, we didn't control it, but indeed we can. It's a way of measuring the drag coefficient, and if I remember well, it has some variations, but not enough to alarm you that there is something that we didn't take into account.
Okay, I'll take one last question
Okay,
from Andreas.
thank you. Can you go please to the slide 17? Yeah, thank you. So, have you considered that your model over there, when you increase the alpha, I mean, how it will match the shape at the end of the loop?
It's a good question because in the equation there is a singularity when the string is vertical. Mm-hmm. So in the numerical resolution we have to solve the bottom part and the top part separately, which is why there is a discrepancy here at the tip. It's not as smooth as a real string.
Thank you.
Okay, thank you all. So now the jury has 1 minute to decide the marks.